This is our fifth lesson in Unit 6. We're going to talk about antiderivatives and indefinite integration. We're going to talk about the process of finding an antiderivative, which is called antidifferentiation. We're going to talk about the family of all antiderivatives for some function is called the indefinite integral of a function. And we're going to look at the function where there's a general solution with a constant of integration. Graphically, here's an idea of that. Let's say we know that a function f has an antiderivative capital F, then there's a family of functions which share the same antiderivatives, and they will differ only by a constant. For example, this purple function is a picture of the graph x cubed plus 5. The antiderivative is 3x squared. Working our way down, the red graph is an example, a picture of the function x cubed plus 3. And then the blue graph is an example of the family x cubed plus 0. In each case, the derivative is 3x squared. Each function only differs by a constant, plus 3, plus 5, plus 0. It's just a translation, but they all share the same derivative, 3x squared. If you apply those basic rules given a derivative, you can see that if the derivative is x squared, the function, the original function, has to belong to the family. If the derivative is 2x, the antiderivative has to belong to the family x squared. So any x squared plus a constant would have a derivative 2x. As in the next example, f prime of t is t squared. The f of t would need to be t cubed, but that derivative is 3t squared, and we want to kill off that 3, so we could do that with a 1/3 t cubed. And we're discovering the power rule here. In this case, y prime is 1 over x squared. So if you think about y prime is x to the -2, we want to figure out how can we get to y. So with a little investigating, we could add 1 to this, because in this case we had power 1. We added 1 to that, and then divided by 2. So in the same way, we could add 1 to that, and then divide by -1, and get the constant is, the function is -1 over x plus a constant of integration. So the family of all the antiderivatives 2x has a general solution as x squared plus a constant. And like I said, we're discovering the power rule as we go along. In this case, the function f of theta, if you think back about derivatives, the derivative for sine is cosine. So the antiderivative for cosine is going to be sine of theta plus a constant. And here we can practice the chain rule. So capital F is, we're going to add 1 to the 3/4. So we have 2/3. We're adding 1 to 3/4. That's 7/4. And we need to kill off that power of 7/4 by multiplying this 2/3 by 4 over 7, or dividing by 7/4. So 4/7 times 2/3 is 8 over 21, and capital F of x is going to produce 8 over 21 x to the 7/4 plus a constant. That's called the power rule for integration. This last example, f prime is e to the x. Well, we know from our derivative unit, that the derivative of e to the x is e to the x. So the antiderivative of e to the x is likewise e to the x. The expression, the antiderivative of f of x with respect to x, is this expression. So the differential dx, this little piece right here, serves to identify that x is our variable of integration, and these two variables need to be in agreement. The term indefinite integral is a synonym for antiderivative. An indefinite integral means that we have a plus c. So the integrand is our derivative. The dx is my variable. This x is my variable of integration that matches my integrand. And my capital F of x is my antiderivative plus a constant. If you think about taking the derivative of capital F, we'll get f prime, which is the same thing as lowercase f in this example. And the derivative of a constant is 0, so that just goes away. So we read this notation as the antiderivative of f with respect to x. And here's our basic rules. If this was the derivative, then the antiderivative is just the constant. If this is, I'm asked to find the derivative of k times x, the derivative is k. The antiderivative of k would be kx plus a constant. And these are just the properties that we know in the differential calculus, and we're looking at integral calculus for the inverse operation. This is the power rule that we've just been discovering. So that's majorly important. If you have some function that's a power function, you can add 1 to the power and divide by the power plus 1. So this is called the power rule. You might notice here that if the derivative of cosine is negative sine, when you integrate sine, the antiderivative must be negative to counterbalance that. And that goes for cosecant and cotangent, cosecant. And then we'll work on these a little later on. So there's our list of rules. Here's a couple of tricks. There's about 4 tricks you want to notice. If you have 1 over cosine squared, we could rewrite that to be 5e to the t, and 1 over cosine squared is secant squared. And knowing that, then we can easily find the antiderivative. So 5e to the t is just 5e to the t. And the antiderivative for secant squared is tangent. The derivative of tangent is secant squared plus a constant. So rewriting a term like 1 over cosine squared can help us out. Another trick would be to multiply or distribute. So if you have a binomial squared, it can be helpful to expand that binomial. 9x squared minus 6x plus 1 is the binomial expanded, and then I want to use the power rule. So I'm adding 1 to the power 2 and then dividing by that power. I'm adding 1 to the power 1 and then dividing by that new power. And I'm adding an x to the first power and dividing by 1. And remember the constant of integration. So to simplify, we have 3x cubed minus 3x squared plus x plus a constant. So this is just a simple power rule, but we needed to distribute first and then integrate second. A third trick is to decompose or separate the fractions. So if you consider each fraction, x squared divided by x to the fifth is x to the negative 3. And the second term would be 4x to the negative 4. And then 5 over x to the fifth would be 5x to the negative 5. And I've rewritten the fractions so that it's easy to use the power rule. In this case, I'm adding 1, adding 1, and adding 1, and adding 1 to each power, then dividing by the new power. So we have x to the negative 2 divided by negative 2. And 4x to the negative 3 divided by negative 3. And then 5x to the negative 4 divided by negative 4 plus a constant. In this case, we have negative 1 over 2x squared minus 4 thirds x cubed minus 5 over 4x to the fourth plus a constant. So I've just moved all of those negative exponents down in the denominator to force them to be positive in this case. Then our last trick is multiple options. So I'm going to expand the numerator binomial as x squared minus 6x plus 9. Rewrite the square root as x to the half power, and then separate each one of those fractions so that we have individual terms as x to the 3 halves, 6x to the positive 1/2, and 9x to the negative 1/2 with respect to x. Then using our power rule, we're going to add 1 to each power and divide by the new power. So x to the 3 halves plus 1 would be x to the 5 halves, and I'm going to divide by 5 halves, which is the same as multiplying by 2 fifths. Then 6x to the 3 halves, but we want to multiply by 2 thirds or divide by 3 halves. So I'm going to choose multiply by 2 thirds as my option here. And we need a little bit better subtraction sign. Then this last example, I'm going to add 1 to the negative 1/2. So we have x to the 1/2 and divide by half or multiply by 2 and then clean that up. So we have for an antiderivative 2 fifths x to the 5 halves, and 3 divides 6 2 times, so negative 4 x to the 3 halves, and 2 times 9 is 18, x to the 1/2 plus a constant. So we can just leave that answer just like that. No need to reduce it down anymore. Let's try a few of these. Let's see. Okay, yes, I was thinking of it the right way. So if I take the derivative of cosine, we have negative sine. This is going to be, I think this is going to be L. So negative 6, and the derivative of cosine is sine, but it's negative. And then by the chain rule, the derivative of 3x plus 4 is 3. So multiplying 6 times 3 is 18. That would be this one, 18 sine 3x plus 4. So working backwards. And 6 cosine, can you find that one? 6 cosine would be negative sine. So by default, it's got to be that one. The derivative of sine is cosine, and the derivative of 3 is 18. This one's going to be letter M, and then by default, the last one is letter K. Next, we're going to look at solving differential equations. This is our last set of examples, I believe, in this lesson. So a differential equation is just a statement about a derivative of y with respect to x. So the derivative of y with respect to x is 3x squared. And the antiderivative is the general solution, which means we have a plus c each time we have a general solution. To solve for a particular, that would mean we needed an initial condition to find the c value. So in this case, f prime of x just means dy dx is 2x minus 1. And if we separate the operators, then dy is 2x minus 1 with respect to x. Then we can integrate both sides, the integral of dy and the integral of 2x minus 1 with respect to x. So the antiderivative for dy is y, and the antiderivative of 2x minus 1 would be x squared minus x plus a constant. This is my general solution. But they have given us an initial condition that when x is 2, y is 5. So we can use that initial condition to solve for c. When x is 2, y is 5. What's c? Find c. So 5 is 4 minus 2 plus c. Our c is 3, which means our antiderivative with a particular solution is x squared minus x plus 3. This is called our particular solution. It solves the differential equation 2x minus 1 at the point 2, 5. This parabola passes through the point 2, 5. In this example, we have dy dx is 2 cosine x. We want to separate the operators to put dy on one side and dx with the cosine, 2 cosine x dx. Integrating both sides to get the general solution, y is 2 sine x plus a constant. We're going to substitute negative 3 for y and pi over 2 for x to find the constant of integration. So negative 3 is 2 times 1 plus a constant. Our constant is negative 5, which makes our particular solution f of x. I'm going to get that from here. This is the general solution. But we know our constant of integration, c. So to put those together, 2 sine x minus 5 is our particular solution. Let's try this one. So we have a parabola where dy dx is x squared plus x minus 7. We're moving the operator dy on the right side to pair up with all the variables of x. Integrate the left and the right. Y is 1/3 x cubed by the power rule plus 1/2 x squared minus 7x plus a constant. That's our general solution. We want to solve for the particular solution. When y is 1, x is 3. Substitute 3 into all the x terms and solve for a constant. In this case, we have 1, and that's 27 divided by 3 for 9, and 9 over 2, and 21. And if my arithmetic is right, my C value is 17 over 2, or 8.5. Therefore, our particular solution, f of x, is 1/3 x cubed. Remember, I'm taking it from this general solution, plus 1/2 x squared minus 7x plus 8.5, or 17 over 2. So putting this general solution with our constant gives me my particular solution. A couple more to go. Okay, letter D is dy, and I'm going to take that idea that f prime is dy dx, move the dx operator over to the right side with all the x variables, integrate both sides. Y is x cubed minus 2x squared plus 2x plus a constant. This is our general solution. Substitute -4 for y and -1 for x to solve for our constant of integration. -4 is -1 minus 2 plus a constant. So our constant of integration is going to be +1, because -5 added to 4 is 1. And our particular solution for this differential equation is x cubed minus 2x squared plus 2x plus 1. We have an entire chapter later on for just solving differential equations. These are just some basic ones. In letter E, same thing, gt, g prime of t, so I have dy dt is g prime of t. So dy on the left is equal to t to the 1/2 with respect to time. So I took g prime of t as dy dt, or dg dt, separating the variables. I'm calling this y. T to the 1/2, we're adding 1 to the 1/2. That gives us 3 over 2. And dividing by 3 over 2 is the same as multiplying by 2/3. And our particular solution comes when y is 6, t is 9. So to find the c value, I like to think about the square root of 2 is, the square root of 9 is 3. 3 cubed is 27. So we have 2/3 of 27. And 3 divides 27 9 times. So this right side is 18. And 6 minus 18 gives us -12 for our c value. So the g of t, you could write capital G of t, or y, is our general solution here. So 2/3 t to the 3/2 plus c, and our c is -12. Particular solution. We're looking for particular solutions. And here we go with our last example. So df dt. So df or df d theta is sine of theta d theta. So if I write df d theta and move the operator d theta to the right side, the antiderivative for df is f, and the antiderivative for sine is negative cosine plus a constant. Remember, this is my general solution right here. Y is 2 when theta is 0, and the cosine of 0 is 1, negative, so negative 1, and added to 2 is 3, so my C value is 3. So the f of theta is negative cosine theta plus 3. And we have our general solution there. So lots of practice here with the power rule and the antiderivative and solving basic differential equations. See you next time. We're halfway through the chapter.